Right, guys, let's get started. Let me first walk you through the question. All right. So, catch 22. One second. Yep. Right. So, what this problem is basically about is that you have a robot. All right. And it can move along the number line in both directions. So it can go to the left of the number line or to the right of the number line, and you always start from zero. Okay. Now, if you look at the question carefully, it says that it's programmed to move forward f meters and backwards by b meters in a straight line. That's a number line. The robot covers 1 meter in t units of time. For now, just keep this in the back of your mind. We won't really need it until the very end. On the robot's path, there is a ditch at a distance fd from the initial position, right? Your initial position here is 0. So to the right side, to the positive side, if that's how you want to imagine it, at a distance of fd, you have a ditch. Similarly, you have a ditch at a distance BD from its initial position in the backward direction. So this is towards the negative side of the number line. This forward and backward movement is performed repeatedly by the robot. All right, so it's going to go forward, backward, and this is the only order in which it can take steps. So you won't have the robot move forward, then backward. All right, it has to go backward once it has gone forward, and it keeps alternating between these steps until it crosses over or falls into a ditch. All right, so the idea is, given the way this robot moves, that is, if I tell you what is the size of the forward step, the size of the backward step, the time taken to cover 1 meter, and the distance from the initial position of both the ditches, the front ditch and the back ditch, you should be able to tell me in which direction or in which ditch the robot is going to fall, if at all it does. Also, you've got to print the time it takes for the robot to fall into either of the ditches. In case the robot does not or cannot fall into any of the two ditches, we're just going to print no ditch. All right. Question is pretty straightforward. We'll get to the graphics in a bit. All right. So I'll show you how the robot moves. It'll make it much clearer. Let's just take a quick look at the constraints to see what all is allowed, what all is not allowed, what do the inputs to this question look like. So if you see here, it says the first move is always going to be in the forward direction. All right, keep that in mind. You have n here is, I'm guessing, the number of steps. Oh no, so n here is the number of test cases, right? So for each test case, we're going to get a value for forward displacement, backward displacement, the time taken per meter, the distance of the ditch FD in the forward and the backward directions, right? So you can have at max about 1 lakh test cases, all right? And each test case will have these five numbers, right? Your F, B, T, your FD and your BD, all right? And it also says that all your input values are positive integers only. So we're not going to end up with any weird combinations of oh, it takes -3 seconds to cover a meter. Nothing like that. All right, so now that we're done, let's just take a quick look at the sample input and output just to make sure what it is that we can expect as input and what it is that we're supposed to give as output. 3 here is your number of test cases, n, and now you have 3 test cases, right? 1, 2 and 3. And for each of these 3 test cases, you're going to have to print a result. You're going to have to print out an answer for each of these test cases. So from what we can see here, this particular test case ends up in an answer saying, oh, it takes 63 seconds for the robot to fall into a ditch, and it falls in the forward direction. So 63F is what we have to print. For the second case, again, the question tells us the answer is 25F, which means it takes 25 seconds for the robot to fall, and it again falls into the forward ditch. The third test case here, slightly interesting, because apparently, according to the question, the robot is not going to fall into a ditch. All right, we'll see in a little bit about what makes this particular test case a little different from the others. Okay, but okay, just to recap, this is what you have to print. All right, no ditch. Make sure you're very particular about the case. Okay, so in most questions, TCS, your CodeVitas and any online compilers or any online judges, right? They're very particular about the case of what you print. So you can't get away with printing lowercase no ditch. All right. So be sure to read the question carefully in such cases. Again, just to kind of wrap this up, 5 cases. You have your 5 inputs over here, 5 test cases, and the outputs are again going to look like a time or an integer followed by the direction in which the robot falls. All right, so let's look at a couple of images. Okay, I've been speaking for a long time, so all right, so let's look at this. Right, this is how I want you to map the entire question in your head. Okay, you're supposed to be able to visualize the question really fast when it comes to competitions like CodeVita. So what it really helps, again, we have a graphic of this over here, but if you have a pen and paper, this is what I would expect you to draw. All right, or this is what I would have drawn when I first read the question. We draw a robot. Make sure you understand how the front ditch and the back ditch looks like, where they are placed. If you can see here, the front ditch is at a value of FD, right? Your back ditch is at a value of BD, away from the center or away from your initial position. You're at 0. And every step that you can take, remember the first ever step that we take in this question is always going to be in the forward direction, right? So you can always take a step F meters long in the forward direction, and when you go back B by B meters, right? Right, so this is how it looks when you start off. All right, you're at the center, you're supposed to take the first move, which is F, that is towards the front ditch. Now once you've ended up making any of these moves, what you end up with is a situation like this. All right, which means after your first step, you're going to get closer to the front ditch, right? You're going to move in the forward direction. Now when you do that, the next step that you can take is only in the backwards direction, right? So you'll be somewhere in the middle. All right, if this is your first step, you'll be exactly at a distance F units from the center. According to this diagram, what it looks like is, if you end up taking another step by F, suppose at some point you can, right? Then it looks like you're going to end up crossing the ditch, but that's not technically true. If you read the question carefully, what is going to happen is the robot is going to fall into this ditch. All right, so there's no way that you can cross over a ditch. You can't jump over a ditch. So if in the case that you're going to take a step in the forward direction and the ditch, you're closer to the ditch than the size of your step, you're going to end up falling into the ditch anyway. All right, so just to recap again, you cannot jump over or you cannot cross a ditch. If you cross it, you're going to fall inside it. At that point, you're supposed to exit your function. At that point, you're supposed to print the solution. Let's actually take a test case for this, shall we? So here you have your nice little robot. It's at the center, and this is what it's going to look like. All right, so my first test case, if we move over to the if we look at one of the sample test cases here, let's pick this one, right? So F is 9, which means in the forward direction I can take a step of 9 meters. In the backward direction I can only take a step of 4 meters. The time it takes for every meter, for the robot to go through every meter, is 3 seconds, right? So 3 seconds per meter. The front ditch, the forward ditch, is at a distance of 13 from the center, and the backwards ditch is at a distance of 10 from the center in the opposite direction. So this is what it looks like. Again, it's the same model that we've been looking at. You have a robot, front direction is 9, back is 4, and your front ditch is 13. So what happens after you make that first step, right? You're always going to make a step in the forward direction as per the question, right? So that's what we do. We end up making a step 9 units in the forward direction. Turns out we're still good. The front ditch is quite a distance away, so we're not going to fall into anything. We're at a distance 9, and now it's the turn for us to take a step in the backwards direction, right? As per the question, you have about, each step in the backwards direction is about 4 units long. So once you make that step, you go from being at 9 to being at 5, right? Because you take a step backwards by 4 units. Now what happens is you're now farther away from the front ditch. All right, earlier you were at 9, the front ditch was at 13, but now you're back to being at 5. Since you've already taken a step in the backwards direction and the robot alternates between both of these steps, front and back, the next step we take is obviously going to be in the front direction, right? So from here, where we're at 5, right, we end up taking a step 9 units in the forward direction, which means we'll end up at 14. But since we already have a ditch at 13, we're going to fall into it, right? So to recap, with this particular set of inputs, 9 in the forward direction, 4 in the backward direction, and the ditch, the forward ditch being present 13 units from the start, we first take a step of 9 meters, then we take a step of 4 meters, and then we can only move 8 meters, right? Because the minute you go from 5 to 13, which is you move 8 meters, the robot is going to fall into a ditch. It will not be able to complete its entire step. All right. So up until now, how many meters have we moved? 9 in the forward direction, 4 in the backward direction, and 8 again in the forward direction. 21 meters is the distance we have traveled so far. If you go back to the question where it says every step takes about, every meter, it takes about 3 seconds for the robot to travel that distance. Let me just quickly go over to the question here. Right. So if you look at the first test case here, 9, 4, 3, 13, 10, 3 seconds is what it takes to travel 1 meter. So for 21 meters, it's going to take a whole of 63 seconds, right? So I'm hoping for this particular input, the output is clear to you, right? 21 meters, 3 seconds per meter, so 63 seconds in total. And the direction, the ditch in which we fall is FD, right? The front ditch or the forwards ditch. So the direction is what we're going to end up printing as F here. Let's go back to our slides. All right, so let's get to the way you would approach this solution. All right, we'll come back to how to take input and output, but it seems fairly straightforward. You're supposed to take the number of test cases is an integer, right? So input that, and then for every test case you have 5 of these space separated integers, right? So your F, D, F, B, T, FD and BD are going to be separated by spaces. Again, take that as an input, and let's see how we would want to solve it. All right. So given this, you ideally first want to handle the easy cases, okay, the straightforward cases. Straightforward cases here could mean, what if within our first step, the robot, before it even makes, even just in its first step, it's going to end up falling into a ditch. All right, that seems like a pretty straightforward case. And when do you think that could happen? If your front ditch is at a distance smaller than the size of your forward step, right? Which means the front ditch, suppose it could be at 5, but you take the first step by about 10 units. So F is 10, but FD is 5. So in your first step itself, you're going to end up falling into a ditch, right? So in that case, you kind of just need one step. So you're going to print the answer and you're going to exit, right? Which translates into this nice piece of pseudocode. If FD is less than or equal to F, you're going to return FD, and the direction here is forwards, right? Again, what you ideally want to do is you want to return FD multiplied by T, all right? Because FD is the distance in meters that you are going to end up taking, while T is the time it takes for you to travel per meter, right? So you know what, let's just keep the whole discussion in terms of the distance that the robot travels, okay? Because when you print the solution, all you have to do is, if you know what the distance is, you just have to multiply it by T at the very end. All right, so in this entire solution approach that we're going to discuss, we're just going to focus on calculating the distance that the robot has traveled. All right, because from there the solution, printing the solution is pretty easy. Another easy case is when you know that it's going to end up in the backward ditch really soon. Okay, so suppose you take the first step forward and then you take another step backward, but within this backward step itself, your robot has ended up falling into a ditch. The way it could happen is, again, I would encourage you to use your pens and papers right now. Not exactly the most easy thing to follow if you're not making diagrams, if you're not following along with a pen and a paper right now. So if you haven't arranged it already, please do. Yeah, so right now, again, we've already done with the case where the robot falls into the front ditch in the first step. Once it takes that first step but doesn't fall into the front ditch, it has to take a backward step, right? The minute it takes a backward step, what's going to happen? If you go forward by say 5 meters, but you end up going backward by say 20 meters, okay? So now on the number line, you are somewhere at minus 15, right? Or you are 15 units in the backward direction. Now, if your backwards ditch is at a smaller distance from the center, okay? Suppose your BD was 7 or 12 or 6, right? Then because of your backward step, this huge backward step that you have ended up taking, you're going to end up falling into the ditch right away. Do you follow? So the first step you always have to take in the forward direction. But if your backwards direction step turns out to be quite large, okay, then it could just happen that the first backward step that you take, you end up falling into a ditch. And if that is the case, which is pretty easy to figure out, your B minus F, right? The size of your backward step minus the size of your forward step is the distance you would have gone along the negative, that you would have gone in the backwards direction by now. If that distance is greater than the distance of the backwards ditch, right? So if your B minus F is greater than or equal to backward ditch, then you know the answer, right? You don't need to run any for loops. You don't need to do anything complicated to get the answer. You know that you would have moved F in the forward direction. Then at some point you would have crossed back to the origin, right? Which means you would have gone forward by F and then you would have gone backwards by another F, right? And then finally, once you are at 0 after having, midway through your backward step, you can only go BD units further before you fall into a ditch, right? So the total distance you would have ended up taking in this case is F plus F plus BD. Alright, this might seem a little confusing, but once you have this down on a piece of pen and paper, once you work through a couple of examples, this is going to feel really intuitive. Okay. Again, while returning, I tend to code in Python, so a lot of my pseudocode is going to resemble Python. Don't worry if you can't do the exact same thing that I'm doing here in C or C++ or Java. Uh, you just have to find a way to set the direction here, right? So for instance, I'm going to set the direction here to be backwards because I know it's going to fall into the backward stage. And the amount of distance that it has traveled is F plus BD, right? Once I have the distance, again, I'm not supposed to print the distance here. If you remember the question carefully, it says print the time taken. So once I calculate my distance, I'm going to multiply it by the parameter t that is given in the question, right? The time it takes per step to travel 1 meter, and that's what I'm going to print, right? So once we're done with that, pretty straightforward cases, the first step you fall into the front ditch, or on your second step you fall into the backward stage. Let's go for another easy case. All right, this is a case where you know that the robot cannot fall into either of the two ditches. Now the only way that that can happen, if you think about it, is if the robot makes a move in the forwards direction and then comes back to the original position, right? Then forever and ever it will keep going from 0 to F, from F back to 0, 0 to F, F back to 0, right? This can happen when your forward step and your backward step are small values, are the equal values, right? So again, just work through it once. If F is the same as B, right? In that case, unless the robot falls into a ditch in its first or second step, what's going to end up happening is it takes the first step, goes to F, second step comes back to 0, and then it keeps taking these steps. There is no way for the robot to move onto any other number on the number line, right? So no matter where the ditches are present, the robot is never going to be able to fall into any one of them. This is another case that the question had warned us about. So the question had said, if we do not see the robot falling into any ditch, we are supposed to print no ditch, N capitals and D capitals. Again, since I'm always returning from a function, what I'm returning here is it takes infinite time or infinite distance, and I don't supply a direction. All right, this pseudocode is my way of telling from my function that the robot does not fall into a ditch. So what I'm going to check at the very end is I'm going to check if the distance returned is infinity. All right, and in that case I'm just going to end up printing no ditch, right? So your code doesn't have to look exactly like this. You could just print no ditch and return or exit. That would be completely fine as well. Now we get into the business end of things. Okay, things are not as simple anymore. We know that we can't fall into the ditch on the first step or the second step, because we would have already passed both of those if conditions by now. The other if condition that we would have already passed is to check whether forwards is equal to backwards, which means we're always almost done with, we can tell right now that the robot has to fall into a ditch in some number of steps. All right, we know that it's not the first step or the second step if we have arrived here, but we know it's some number of steps. And the reason why it has to fall into a ditch, if you think about it, is that if you take these steps in terms of pairs, right, you move forward by F meters and you come backwards by B meters, and F is not the same as B, then every time that you make these two steps together, right, or one after the other, you end up at a net distance, right? So if I were to go forward by 9, come backwards by 4, then my net distance or net displacement here is 5, right? Because then from 5 I can again go back to 14 and then I will come back to 10, right? If I go forwards and backwards, from 10 I can go to 19 and I will come back to 14, come back to 15, right? You go back by 4 units. So again, if we are able to make two steps at a time or one after the other, then we'll always move by this by the difference in the size of the forward and the backward step, right? By our net difference, by our net displacement, which is 5 units. All right, in this case, if your F is 9 and your B is 4, different cases, your net displacement is going to end up being different. Another thing to note here, if your B is greater than F, all right, so suppose your F is 5 but your B is 20, okay, then if you think about it, your net displacement is minus 15. All right, so if you are at 0, you'll keep going minus 15 at a time, every time that you're able to make both of these steps and not fall into a ditch. We'll come back to that case later. It's not tricky. Actually, if you handle the case where you know that the robot is going to fall into the front ditch, then the backwards ditch case is pretty simple. Okay, it's a small extension of that case. So now that we've handled our easy cases and that one case where we know that the robot won't fall into a ditch, let's look into those inputs for which we know absolutely certainly that the robot is going to fall into the forwards ditch. The way that's going to happen is if your net displacement in the forwards direction is positive. Okay, so if your front step is bigger than your backward step and you don't end up falling into a ditch in either one of the first two steps, then you know you're always going to end up falling into the front ditch. Okay, because you're always going to end up making a net move of, in the example that I spoke of before, always a net move of 5 units. Okay, so at some point, no matter how big your FB is, at some point you're going to end up falling into the front ditch. Okay, so just to kind of bring everything together, we now know in case that my front step is bigger than the back step and my robot does not fall into a ditch in my first couple of steps, it's always going to end up falling into the front ditch. We also kind of understand the concept of a net displacement or a net distance that we travel every time we go F comma B. This slide kind of recaps what we just discussed, right? Now, in our original test case, where we had the front ditch at 13, at a distance of 13 from 0, you would think that since we need to make 5 units is our net displacement each and every single time, then we would kind of need what, 3 such pairs of F comma B, go front back, front back, front back, and by the time we do that, we would have crossed 15 meters, which means we would have fallen into the ditch. But the thing is, it's not exactly that, is it? So when you make your first move, right? Let me just quickly go back to the diagram that we had here, right? So it's the same, right? The front ditch is at 13. Your front move is 9. You move backwards by 4 units. The first move that you end up making is going to bring you here. It's going to bring you to 9, right? The next move is in the backwards direction, which is going to end up bringing you to 5. Now what happens when you're there is that you're going to end up making a move in the forward direction, right? But when you do that, you already fall into the ditch. Okay, there's no way for you to go to 14 and come back to 10. All right, I hope you're with me up until this point. The idea was that since we know the net displacement, can't we just move by 5 units every time, and that's how we come to our answer? That's not the case. All right, because at some point you're going to be 9 units or lesser away from the front ditch. in which case if you move in the forward direction, you're going to end up falling into the ditch. Okay, there is no way for you to make another backwards move. All right, keeping that in mind, where we end up now is here. Okay, ideally you would want to keep moving the robot forward by your net displacement amount. So you would want to move in increments of 5 until such time that you know that the next move is going to land you in the forward stitch. Okay, so my robot, I'm first going to move it by 5. Okay, because I know that my front ditch is bigger than my front step, which means it's going to go front, then back, and then front, and then back again, right? So I'm going to move 5 units. I'm going to keep my robot at 5 once it has done F comma B, and then I'm going to check, is moving in the front direction going to throw me into the ditch or not? All right, turns out it will. If I'm at 5 and I move in the front direction, I'm going to end up in the ditch, right? If that was not the case, okay, suppose this guy was at 23 units. All right, suppose the front ditch was at 23 instead of 13. All right, in that case you would have gone from 0 to 9, back to 4, back to 5, then to 13, then to 14, back to 10, then to 19, back to 15. Now that you are at 15, you're going to end up taking one forward step by 9 units, which is 24. But your backwards ditch here, your front ditch here is at 23. So that one front step is going to end up putting you inside the ditch. All right. So you would keep moving by increments of 5s. You would go from 5 to 10 to 15. And at every time you were going to check whether the next step is going to make me fall into the ditch or not. All right. The straightforward way to code this up is to just write a for loop. All right. In the for loop, you can simulate each and every one of these steps. All right. So my for loop could be make a forward displacement, make a backward displacement, and then I would keep looping until I either fall into the forward or the backward stitch. That gives us the answer. The problem is the constraints of the question do not allow you to do that. All right. So let us quickly go back to the constraints once again. If you see here, while it says that the front ditch and the back ditch are greater than 0, they are positive integers, it doesn't really tell you how large or how small these values can be, right? So if suppose your front ditch was a huge number, okay, suppose 10 to the power 7, you're going to have to make those many moves in your for loop. All right, and at that point it just becomes a really inefficient solution. You're going to get time limit exceeded, all those kind of errors, right? Your program will not run in enough time to tell you the answer. However, if you've followed along so far, you might wonder that since we already know that we keep moving in increments of the net distance until we fall into the ditch, why can't we just simply do a division, all right, or use the modulus operator? Can we do something with those operators instead of having to do a for loop, okay, and simulate each and every step? If you've thought along the same lines, that's pretty great, because that's exactly what we are supposed to do, right? So this is what you would ideally want to do, right? Let's first figure out how to reach or slightly cross a distance fd minus f. All right, so suppose your fd was 13 and your f is 9. So you first want to understand how do you get close to that number, okay, that number which is 4 in our case, 13 minus 9. Because if you get to that 9, if you get to that 4, or if you slightly exceed it, if you get to 5 or 6 or 7, you know that in the next step it's going to exceed or it's going to cross FD, right? So to prepare yourself, just before you take that one step, that one forward step, where roughly where it is that you should be able to reach by taking these net increment jumps, right? So let's go with FD minus F for now. It's guaranteed that in the next step we fall into the ditch, right? Coming back to the pseudocode here, okay, it's slightly more involved than what we had last time around. We'll start off with a variable called meters. Meters just keeps track of the number of meters we have traveled up until now. df is our increment size, is our step increment size, net increment, whatever you want to call it. Let's keep it to f minus b. Since we had this thing at second, yeah, since our f is 9 and the b is 4 here, our df is going to end up being 5, right? And don't get confused by the name of the variable here. I say distance per step. The step here is a combination of both front and back. So if I go front and then I come back, what is the total distance I have covered by then, right? So that is what a step means in this particular part of the pseudocode. So you have your distance per step is f plus b, and at the end of taking this step, this combined step, you will be at df units, okay, this net displacement from wherever you were originally. Now if you look at this carefully, right, fd minus f, so what this tells me is, again, so the distance I need to be at just before I take my final step in the forward direction, okay, that is fd minus f. That's the distance you want to be at just before you take a step in the forward direction. If that modulo df is equal to 0, okay, which means you can get to that value just by taking increments of df, okay. So our df here was 5, right? So if it happened that the front ditch minus the last step that we are going to take is a multiple of your net increment, okay, then you're pretty much at the solution, right? Because if you divide fd minus f by df over here, you're going to get the total number of these combined steps, okay, this f comma b pair. So front back, front back, front back, you'll know exactly how many times you have to go that route, and then all you have to do is add another distance of f so that you can fall into the ditch, right? That's exactly what we end up doing here. Number of full steps, this is the number of full steps, that is the pairwise step that we take, and the distance in terms of meters that we have ended up traveling is your number of full steps into distance per step. So in each one of these pairwise steps you travel f and then b, right? So you travel a total of f plus b in each of these combined steps, at the end of which, since you know the number of full steps that you have ended up taking, you end up multiplying both. This tells you your f plus b plus f plus b plus f plus b all the way until the last step. And what is the last step? Your last step is just a step in the forward direction, right? Here meters is going to tell you the total distance that the robot has traveled before it fell into the ditch, right? Just one second, I'm going to drink some water. In the meanwhile, can you pick another test case? All right, let's go with this one. So let's go with let's go with this. All right, so you take a step 9 units in the forward direction, 7 in the backwards direction. Your front ditch is at 11 and your backwards ditch is at 13, right? So if you were going to handle this case, right, 9 is your forward, 7 is your backwards, and your front ditch is at 11, right? In this case, you already know that you're going to end up in the front ditch, right? Because you're not going to end up in the ditch when you take the first move. You know that f minus b is greater than 0, which means the robot is not going to oscillate infinitely, and at every pairwise step it is going to make a net increment in the forwards direction. So you know it's going to end up falling into the front ditch, right? So if you followed along with me so far, this is how the robot is going to move, right?
Slides.
So 1 second. Yeah, so from 0 you go to 9, you take a step in the forwards direction. From 9 you go back to 2 because you took a step in the backwards direction. From 2 you take a step in the forward direction and you end up at 11, and this is where it ends. Why? Because the forward ditch was at 11. So the amount of time that you have ended up spending on, let's first calculate the distance that you have taken, is 9 plus 7 plus 9 again. Alright, so this turns out to be 25 meters, and according to the test case, according to the the case given in the question, if you notice, the time it takes to cover 1 meter is exactly 1 second. So since we've covered 25 meters and at every step we take, it takes us 1 second to take 1 meter, 25 seconds in the forward direction, right? Now suppose your test case was slightly different in the sense that your front ditch was, say, at 13, right? So from here you would again go back. You would go back to 4 in the backwards direction. Let's keep this to be 12, right? And from 4 you know that you're going to end up at 12, right? Once you take a step in the forward direction. And again, the distance you would have ended up traveling is 9 plus 7 plus 9 plus 7 plus the last one, you only travel 8 units, all right? Because from 4 you go to 12 and you fall into a ditch. So according to our pseudocode, what is it that we should have been watching out for? We should have been watching out for fd minus f, right? Because this is the distance to which I have to get to, so that my next step in the forward direction is going to put me down into a ditch. All right, so fd minus f here is 3. So until I come to 3 or I cross 3, there is no way that the next step is going to bring me into a ditch. So this is what I want to watch out for in every iteration. All right, in every pairwise step, this front and back motion, I end up going 9 minus 7, which is about 2 units, right? Always 2 units in the front direction. So that's what we're going to do, right? So we're going to move 2 units in the front direction, 2 units again in the front direction. But at this point, we will already have come here, 4B, right? So this is your 2 units in the front direction. Again, 2 more units in the front direction. By this time, once you have come to 4, you've already crossed FD minus F, right? Which means the very next step that you take is going to put you inside a ditch, right? So we're supposed to be counting the number of total increments that we took. So we took 2 full steps, front and back. And each of these full steps would have taken about 16 units, 9 forward, 7 backwards. And then finally, wherever it is that we were, okay, which means, say, num steps into distance per step, all right, your FD minus this value is the distance that remains. Okay, so here, since the number of full steps would have been 2 and the distance per step, or here the displacement per step, right, this also turns out to be 2. So we are currently at a distance of 8 units away from the ditch, right, which means in one step of 8 units we're going to end up falling into it. So that is what you would have put over here, right? And if you notice, this value is the same as this, right? So instead of having to simulate this front and back motion inside a for loop, we're going to be a little creative. All right, we're first going to try to find out, a way using the division or the modulus operator to get to this value fd minus f, right? And once we get there, we know what is the remainder of the distance that we have to travel, right? So once we find out the number of full steps that we can take to come to this value, or slightly exceed it, we're good to go. Just for the sake of completeness, let's take a bigger example here. 9 and b are going to be the same. Let's keep the fd to be 15. Yeah, let's do that, right? So once fd is at 15, we go backwards by 7 units. So you'll end up at, so over here from 4 backwards you go to 13 forwards. From 13 forwards you're going to go to 6 backward. From 6 backwards you're going to go to 15 forwards, right? And at 15 you've ended up in the ditch. Now what is my fd minus f over here? My fd minus f is 6, right? So I'm going to first find out the number of full steps I can take to get to 6 or slightly beyond 6. That's pretty simple. I just do an integer division of 6 by, the net displacement per step, which gives me 3. Now 3 is coincidentally the number of full steps that we've ended up taking. 1, 2, 3, right? And after taking 3 full steps, where are we? We are at a distance of fd minus 3 into 2, right? That's how far away we are. And we know that if we take even one more step, we're going to end up in the ditch, right? Which means this fd minus 3 into 2 is going to be the step size of our last, the last distance that we have to travel. Coming back to our pseudocode, let's see how this has been represented there, right? I've broken it apart into an if and an else condition. You might not need to do that. Actually, if you want to get a little clever with this code, you don't really need an if and else condition over here. All right. Just for the sake of being able to explain the two cases to you nicely, I broke it down into conditionals. So the first step is where we know, the first if is where we go to when we know that f is the size of the step that we are going to take. Otherwise, what we are going to do is we're going to end up exceeding that fd minus f, right? So what we end up doing here is we take the integer division, right, and we take the ceiling of it. So for instance, what would happen is if your fd minus f, let's go back to that the example that we were working on. Suppose we keep our fd as 14, right? So what happens here is your fd minus f becomes 5. Okay, since in each step you end up incrementing your distance by 2, your overall displacement by 2, you're never going to end up at 5, right? You're going to end up at 4, then you go to 13, and then you come back to 6. Okay, but since 6 is greater than 5, we know that at this point, the first point after which you cross fd minus f, the next step that you take is going to end up in the front ditch, right? So here what we would want to do is ideally this. right? 5 divided by 2 plus 1, which would again be 3 here because we're considering the integer division here, right? If not, the easier way to do is to just take, the ceiling, or to round it upper. Okay, so if you had 6 divided by 2, it would give you 3. If you had 5 divided by 2, and again converted this into an integer, then again it would give you 3, right? So you want to find out the full number of steps that you can take, and once you've done that, this is just this is a way of doing the whole ceiling thing that I just showed you a couple of few seconds ago. We calculate the remaining distance as we've been doing so far, FD minus number of full steps into the net displacement per step, and then you're going to find out how many meters your robot has ended up traveling, right? So your full steps into the distance per step, which is different from displacement. Okay, distance per step is F plus B. So your number of full steps into distance per step plus your remaining distance. Okay, that's what you're going to end up returning. Return these many meters in the forward direction. And with this, the only other case that we have left to do is what happens when we know that the robot is going to fall into the backwards ditch. All right. Let's just take a break of 2 minutes here. Why don't you guys sample this test case for now? 1 second. Yeah. So yeah, let's go here. Let's try to do this case 8, 4, 7, 11 and 22. All right. So suppose this is the case that we have to go. Given that, F is greater than B and your net, your displacement is, your front ditch is much farther than, your F. So you're not going to be able to make that in the first step. Given all of that, see if you can come up to this number 133 using, a pen and a paper. Let me get back to you in just 2 minutes. Meanwhile, focus on this case. This is what you should get as output. All right. So run through all the calculations that we have done so far. Make sure you get 133 as well. Right, guys. Let's get to the code then. It's pretty much the pseudocode that we've been discussing so far. Again, as I told you, I generally prefer coding in Python. So all of my examples that the code that we're going to write is going to be in Python again. So let us start with something like this. All right, so first we're going to worry about taking the input. So you have your n, which we take as an integer, and then for each of these test cases, this is how I end up reading in all 5 values. What this does is it takes the input, removes any spaces at the front or the back, and then splits it, right? So at the end, all you get are strings, right? And for each one of these 5 string inputs that we're going to get, I'm going to convert them into an integer, since that's exactly what the question tells me. Once I do this, this array is going to have 5 values, and Python allows you to, really conveniently get 5 values out of, an array of 5 values this way, right? So this is going to be a of 0, a of 1, a of 2, a of 3, a of 4. Now that we have that, what we're going to end up doing is I generally try to keep my main solution in a separate function that I call solve, right? So let's Go with this. And this method solve is going to return the distance and the direction that the robot ends up traveling before it falls into a ditch, right? So given that, what I know is I can always do this. One second. Right. So once I know my distance and the direction, I know that the time it takes for the robot, I can just calculate as, distance into t. Um, and if the time is infinite, as we were discussing in a previous, the sample case, we know it doesn't fall into a ditch. So we print out no ditch and exit. Otherwise, we're going to print out time, which is again distance into t, and the direction, right? So let's see how you would implement the solve method. If you remember our original discussion, we want to handle the easy cases first. So the easiest case here is going to be, in the very first step, we know it's going to fall in the forwards direction. So if your front ditch is smaller than the size of your step, you just return, front ditch, the distance, and then you return the direction f. If you can find out that it falls into the backwards ditch in the second step, again, this is consistent with the pseudocode we have discussed so far. This is what you're going to end up printing, right? And finally, we're going to end up tackling the case where we know that the robot is not going to, fall into a ditch. So we know it doesn't fall into a ditch in the first or the second tries, and then it falls into a ditch. The front and the back steps are equal, so it's just going to oscillate, right? It can't fall into a ditch. If I return infinity over here, once the test case has been solved by this function, my time becomes infinity into t, which is again infinity. So I'll say if time is infinity, then print no ditch, right? This is my way, my function's way of telling the rest of the main function that the robot doesn't fall into any ditch. Now, once we've handled these three cases, what you want to do is we're going to, handle the case where we know that the robot is going to fall in the forwards direction, right? So this is what we're going to end up doing. We're going to say meters is 0. We start off, having traveled no distance. This is our net displacement, and this is the distance per step that we take, okay? Every pairwise step, we travel f plus b meters. The surrounding if condition of sorts over here should ideally be if your f minus b is greater than 0, right? That is when you want to do all of this magic. If your f minus b is greater than 0, yep, that is when you're going to do exactly this. You're going to return the meters and the direction. The only case that remains after this is if b minus f is greater than 0. Now, what is different about this case? I told you there was something slightly different, right? The difference is in the forwards case, you always start from 0, right? But in the backwards case, when you know that you're going to end up in the backward ditch, you don't technically start from 0, right? You always take a step in the forward direction. So from 0, we would have moved 9 units to the front. But if our catch-22 test case was such that we end up falling into the back ditch, right? Then we always have to remember that you have to take care of this one case, this case that you've already traveled 9 meters, and then you're going to have to come back by that 9 meters to reach, wherever it is that that you're supposed to go to. So after the backward step, suppose backward step was say some 20 meters long, then the front step 9 meters, backward step 20 meters, which now means you are 11 units in the backwards direction. But the total distance that you have traveled, this this meters, right? This is what we are using to keep track of the number of meters we have traveled so far. This has to be updated accordingly. Okay. Now I'm going to leave this part of this part of the question as an exercise for you to implement. All right. Just to kind of quickly go through and check whether what we've written so far gets us the answer or not. Let's do Python 3, my solution.py. Actually, before that, let's just quickly check what our small test case is. So, okay. Suppose we just do Python solution.py. 1 second, it says expected and indented block, is it? Okay. So I'm just going to not handle this case. So let's go with 5 test cases for now. Let's go with 5 test cases. So let's start with the easy one. Front and back both moved by 4. The front ditch is at 8, the back ditch is at 9. So for this you would expect to get 1 second. Yeah, this is where I messed out, right? So for this particular case, your 44184, you don't fall into a ditch, right? Let's pick out another easy case where we know it's going to end up falling in the front ditch. So let's do 8, 4, 7, 11 and 22, right? The one that we've been talking about so far, the one I gave as an exercise. So you have 8, 4, 7, 11 and 22, right? Okay, for some reason this gives us 133 and none, right? Because we know we're always going to go in the forward direction, right? Right, 133 and F. Make sure you return the direction in both of these cases. So if F minus B is greater than 0, you know it's always going to end up in the front. Here you will again have to return something like, meters comma back, right? And the exercise is to calculate meters, right? So what you can see right now is for any case that we know that is going to end up falling into the front ditch, we end up finding the answer, right? The only case that remains is what happens if it goes into the backward ditch, which again is pretty much the same as what we did here. Okay, you can simplify this a bit further if you want. Just keep in mind that your first step is already in the forwards direction, right? So we're already at F by the time we take our first step in the backward direction. That's about it. Let's just, for completeness sake, let's just quickly go through the thing once again. This is how I take my inputs. I generally like to keep the solving function separate from the main function so that it's clean, so that I can I can only focus on short functions at one point of time. Once I get my distance and my direction from this function, I calculate the time that it takes. If it's an infinite distance or infinite time, I'm going to print no ditch, or else I'm going to print the time followed by the direction, right? This is Python 3 syntax. If you have not seen this, do not worry. Do it exactly as you would do by concatenating strings using the plus operator, that's perfectly fine as well. If we come back to our original solving function, we handle the two easy cases at first. Then we handle the case where we know that the robot is not going to fall into a ditch. Then we handle the case where we know it's going to fall in the front ditch. All right. This is the case where we know it's going to do that. You calculate the number of increments that, the pairwise steps that you can take, followed by the remaining distance that you have to travel. Once you're done with that, the only case that we have left to do right now is the backwards case, right? The trick over there, or the slight change that you have to make, is that the first step is always in the front direction. So you have to, every time you go front back in the previous case, here you have to go back front, back front, back front. Okay, that is going to be your pair. So make that initial displacement, and the code that you have written here, you should be able to tweak it slightly so that this front back becomes back front. Okay, and those are the pairwise moves that you're going to end up making. Once you're done with that, you would have solved your solution. So that's pretty much it from my side. Hope you guys enjoyed solving this. It's a long problem, okay, having a lot of test cases. So ideally you want to keep your functions short. Okay, in a long question like this, you don't want to put everything into one function. In a long question like this, the other thing you're supposed to do is to think of small easy test cases that that are obvious, that are easy to code up. All right, get rid of the small test cases and then start to think of what the other two big test cases can be, right? Hopefully you can take away some things about how I write code from here, and implement or improve the way that you do it. Don't forget to like, share and subscribe. I hope you found it useful. I hope your friends found it useful.
So we have a couple of questions.
Okay. Right. So we have a couple of questions here.
Okay. So the first question, and I would request you to repeat the question so everybody can hear.
Sure.
Okay. So the first question is, you've written it in Python. I don't know Python. Can I still solve this problem?
Oh yeah. So the question that one of our batchmates is asking is that they don't know Python, all right, and the entire code that I have shown to you so far is kind of in Python, right? The pseudocode also looks like Python. You can do this in any language that you want. Okay, there are going to be some very small tweaks. Okay, you know what, let's just go through the things that I would think would change if you were to do it in C++. Your input functions are going to change, obviously. In C you would use a scanf, in C++ you would use a cin, Java you would use a system.out.println. The way you take inputs for these five is going to change. Java you can just do a scan.nextInt nextInt. You have to take input with scan.nextInt, a scanner and nextInt in Java. For C++, again, it's pretty simple. You just do a cin 5 times. You do a scanf with %d 5 times. Apart from the inputs and the outputs, nothing really changes, right? Instead of returning this function, okay, in C++ you could just keep it as void. You could keep it as an integer, distance. You could return an array if you wanted, or in the parameters to this function solve, you can pass the pointers to an integer and a character. Again, complex approaches, you don't have to worry about any of that. Even if you don't write a completely new function in C or C++ or Java, you can keep all of this code over here, right? Inside your main loop, inside your main function. Then you just call return 0 or whatever when you want to exit.
Right. So Rahul Priyadarshi asks a question. Can you please explain the input line in main function? Because we are short of time, can you just explain it in 2 minutes what's happening? And can you just repeat the question?
Oh, all right. So someone's asking what this function input does on the first line, on the 35th line of my
No, so
screen.
that's the 38th line. Yes.
The 38th line.
How
Oh,
will
okay, right. So see, all it's doing is this input is going to end up giving you a string, right? It's a string comprising of the entire F, B, T, FD and BD, right? One line of the test case. Here I am stripping it of the spaces in the front and the back, right? So if there was a new line character or something in this string input, I am removing it. Once I've removed it, I am splitting it, right? So just by printing this input, strip and split, this is going to give you an array of strings. Okay. For each element in this array of strings, I convert it into an integer. This is a feature of Python called list comprehension. Again, C++ and Java users, there's nothing like this for you. Sorry guys, but again, you don't have to worry that much about it. You just do a cin or a scan next int, you should be fine. You don't exactly have to do something as tricky or complex as this.
So one last question. You've described the algorithm for this one. Are there similar questions in CodeVita, or is this the only type of question like this in CodeVita?
So turns out there's this question called drunkard's walk. So the question that someone asked was, are there similar types of questions to this, or is this like a standalone one-off question? So it turns out a lot of questions are kind of similar. So you have something called as drunkard's walk. I'll have to check which year it was in. But yeah, you have similar questions. So in some cases, they're going to ask you to, output the time. In other cases, it's going to be much simpler. They don't care about the total distance. They're just going to say what are the number of steps taken. A lot of variants to this question. It's a very popular aptitude question as well. If you've heard monkey climbing a pole, it can climb up and then it slips down. So yeah, so this question has been pretty popular. A couple of variants you'll find on the previous CodeVita question. You can find most of the variants of this, Drunkard's Walk and the others included, on the Edyst platform, right? So come see us there. There are a lot of questions that are kind of similar to this, all right? Or you can at least pick the same ideas. You can practice on the Edyst platform as well. Each past year question of CodeVita is there for you to solve. So yeah.
So two last things. One, is the full explanation of this there on Edyst platform in a reading format? And two, if I have doubts, who can I reach out to? How can I reach out to you?
Okay, so the full explanation of this question is there on the Edyst platform in form of a reading material, right? So the entire dance that we did today with the slides and with the robot moving back and forth, we've actually ended up making like a collection of nice helpful GIFs, okay, to help you, a couple of animations to help you visualize this problem. So the editorial or the solution to this in a text form, in a reading format, you can find on the Edyst platform. um, Actually, you know what, let's just go ahead and check that out. The second kind of concern or question that some of you might be having is, what happens if you get stuck in a question like this, or in a similar question? So here you see we have drunkard's walk, we have Catch-22, the coding question that we did, and this is the reading material that we have for the same question, right? So you have your illustrations, we talk about the edge cases, summarizing the edge cases, then we go to the main, the front and the back. So for some of the more important questions, you generally find in-depth text or video solutions, editorials to these problems. They're slightly different in the sense that we don't just talk about one problem, all right? So if we talk about, say, Catch-22, we're going to give you helpful ideas that you can apply to other problems, right? For instance, drunkard's walk over here. a similar question, if you solve Catch-22, it's kind of like a tougher variant of this problem, right? If you have doubts, you always have, it's a thriving community. You have about, you can see that Aneeq generally tends to have close to, 20-30 people um, asking him doubts. I'll be there on the platform, but more importantly, you'll have your batchmates, right? You'll have an access to a really friendly group of people who ask similar questions that you do. We have forums where you can post your questions, right? You can reach us out. You can reach out to your batchmates and to the Edyst mentors on chat. So I would say you have a lot of ways of um, getting help. You just have to kind of keep asking, right? So if you see Aneeq on chat, ping him there. If not, use the forums. You can get your questions answered there. So that was all, guys. I've taken up a lot of time today, but hopefully you found this whole experience interesting. There are a lot of small points that we discuss about how to write code that should also help you. I'll see you later. Please don't forget to like, share, and subscribe. Have a great day, guys.